Okay, so the next thing we want to talk about is the idea of a directional derivative. And in the last section, what we did was we said, hey, if we've got some surface in 3 space, and we go to some point on that surface, we could say, hey, if we nudged a little bit in the x direction, here's x, how would our y values change? Okay, so we imagined the curve passing through like this, and we said, as we nudge a little bit in the x direction, what do our y values do? Or excuse me, what do our z values do? And in this case, our elevation would be dropping a little bit based on that picture I drew. And that was our partial derivative with respect to x. And we could also say, wait, let's nudge a little bit in the y direction, and maybe that passes through some sort of, that's what the surface looks like there. And in this case, as we move a little bit in the positive y direction, what would our height be doing? What would our elevation be doing based on this little picture that I drew? It'd be increasing, right? So that was assigning looking at 2 particular directions. We could say, let's nudge a little bit in the x and look at how our z values change, or let's nudge a little bit in the y direction and see how our z values change. What we want to do now is we want to step in any old direction and ask the question, how do our z values change? Okay. And we'll look at that here in just a second. We'll look at a better picture here in just a second. But that's where we're going with this. Okay. So we're going to ask the question, if we move along the direction of some vector v, what is going to happen to the instantaneous rate of change to our function? What's going to happen to our change in our z coordinates if we move along the direction v? Okay. So to do that, we're going to introduce this new character here. This is our directional derivative. Okay. There's different notations for this. This is the notation that our author uses. Okay. And the way you interpret that is you say, how does f change as we step in the direction of the vector v? Okay. All right. Before we go any further, the author does this, and most authors do this in order to make the proofs easier. We only think of we think of our directional derivative as always taking the directional derivative of f as we step in the direction of u, but we let u be, we fix u to be, or we say that u has to be a normal vector. Or not a normal vector, I'm sorry folks, a unit vector. Okay? So we're only going to do this for unit vectors rather than any old vector. So although that's fine, we're going to be using this notation here, and I'm sorry that u should be bolden. All right, so let's see if we can clarify all of this with a picture here. So we're gonna look at the domain ordered pair a comma b. That's the domain value, right? Okay. This is our surface here. Living above this is a surface z equals f of x, y. So that's our surface. But we're looking at the domain value a comma b, that ordered pair in the domain space. And so what we're going to do is, rather than just nudge in the x direction, or rather than just nudge in the y direction, we're going to nudge in some direction u for a unit vector u here, and ask, if we move in that direction, how do our y values change on our surface? Okay. So one way to imagine this, and this is probably the easiest way, is go ahead and form a plane that matches, that's perpendicular, or let's see, a plane here that runs perpendicular to the xy plane, and also moves in the direction of that vector u. So you can see this plane q here that's slicing through our graph of our surface. And so when we slice this plane q through our surface, notice that it forms this curve here that the author's drawn in black, that curve C. Okay. So we step in the direction of u, And we can imagine that once we've assigned that direction, we've got a plane perpendicular to our xy plane, perpendicular to our domain, passing in the u direction, and that slices our surface, giving us this black curve here. Once we've got this black curve, we can do essentially Calc 1 on this black curve. Okay? So the strategy is to take, here's the ordered pair, well, here's the ordered triplet, A, comma, B, comma, f of A, B. Okay? And then if we nudge along some distance h, so think of h as a small quantity, although here we're drawing it bigger than 1 just so we can imagine the picture. Okay? So h is some quantity that we're multiplying our unit vector by, so think of it as stepping h units in the u direction. Okay? That's going to give us some new ordered triplet. That's going to be the vector a plus u1h, comma, b plus u2h, comma, and then f of a plus u1h, comma, b plus u2h. So that gives us this new point on the graph. Okay? I know this diagram's getting a little bit cluttered, but once you've got 2 points and you're thinking of the curve along the surface passing through those 2 points, what can you compute? You can compute the slope of the secant line between those two. Let's see, I got a chat I think popped up. Hang on. No, maybe not. Okay, never mind. Okay, so once we've got a slope of a secant line, then to find the instantaneous rate of change in that particular direction, we simply take the limit as that step size, that h, goes to 0. So this part should seem kind of familiar. It's like what we did with our partial derivative with respect to x or our partial derivative with respect to y. The problem is that we're holding neither of the two x and y coordinates constant. Okay? Which makes it a little bit more complicated. All right, so this all gives us our definition of the directional derivative, which we give on the next page. Folks, I'm going to pause this here. All right, let's give it a shot here. So here's our pointwise definition of the directional derivative. Okay? So the directional derivative of f at the point AB in the direction of u is given by this limit definition here. Okay? So I'd like to go ahead and compute one of these using our limit definition. So here we've got the function f of xy is equal to x times y minus 1. And the directional derivative, we want to compute that at the point 2, 3 in the direction of v, where v is the vector 5, 6. Okay, so first of all, in order to do this, what's the first thing we need to do? Based on the way our author's given the directional derivative definition. Yeah, so we need to go ahead and find an equivalent unit vector. So we could say that u is equal to, and then if we were to find the magnitude of this, it would be 1 over the square root of 5 squared plus negative 6 squared times the vector 5, negative 6. Okay. So if we clean that up, that gives us, that's 25 plus 36 is 61. So this gives us 5 over the square root of 61 minus, for the first coordinate, and then minus 6 over the square root of 61 for the second coordinate. Okay. All right. So we want to find the directional derivative in the direction of this unit vector u, so 5 over the square root of 61, comma, minus 6 over the square root of 61. For this function evaluated at the ordered pair 2, comma 3. So now I'm just going to follow this definition, okay, which should look a little familiar. It's still taking, still computing the slope of a secant line, and then we're taking the limit as this step size goes to 0. So that should look a little familiar. This is the limit as h approaches 0 of f of 2 plus 5 over the square root of 61, comma, 3, oops, I forgot my h there, comma, 3 plus negative 6 over the square root of 61, h, minus f of 2, 3, all over h. Okay? Now, normally, folks, computing this would be a real chore, but it's not going to be too bad in this case because everything's raised to the first power, so we won't have too much work to do on this. So this is the limit as h approaches 0 of, and then if we actually plug into the function x times y minus 1, that's 2 plus 5 over the square root of 61, that's our x-coordinate, times y, which is 3 plus negative 6 over the square root of 61. I keep dropping those h's. H minus 1 minus parentheses 2 times 3 minus 1 all over h. Okay. Folks, I apologize, my handwriting's a little bad there. Is that tracking?
Should that be f prime of 2 comma 3 equals all of that?
No, it should not. Does it look like it up there? No. So remember, this is so remember, Dustin, and I'm going to jump between pages now. We're computing the slope of this line right here in this particular direction. And so we're looking at the change in the height between these 2 points. So that's this functional value right here, and we're going to subtract from it this functional value right there. That gives us the change in the height.
Okay.
And our change in width is simply the actual distance between these 2 points, which is h.
Right. I get that, but like when you go back to the other page, this whole limit expression is the slope, right?
Yes, when we're done, yes. So are you asking why don't I put a prime there?
Okay. Actually, no. I see what it is. Yeah. This is the function d. Of u.
Yeah. So think
that function. Okay. Yeah.
And so think of
really
I see what you're saying. They've kind of got spread apart. Think of that d as the derivative, the directional derivative of, and then what follows.
Right. I didn't realize that d function was attached to that f function.
Yeah. Sorry about that. There we go. Yeah. Good.
Thanks.
Other questions, folks? Okay. So we can clean this up.
Sorry, could you scroll back up just a bit? I'm going to get a picture.
Okay.
All right, thank you.
So now we're going to continue with this limit. We've got the limit as h approaches 0. And if I FOIL out, folks, I'm not going to take a line to write this as, this would be a 2 plus this. So I'm just, well, no, I better. 2 plus 5 over the square root of 61h times 2 plus negative 6 over the square root of 61h. And then this whole thing is minus, let's see here, that'd be minus 4 all over h. So we've got the limit as h is approaching 0 of, and then I'm going to FOIL this out. This gives me 4 minus, let's see here, I don't want to write this. I want to write this as 2, 3, that's 2. That's 2. So 4 plus 2 times negative 6 over square root of 61h. Plus 2 times 5 over the square root of 61h, And then the last term would be minus 30 over just 61, no square root, h squared minus 4 all over h. This cleans up. Notice that my 4's cancel here. So this cleans up to be, that would be minus 12 and a positive 10. So that cleans up to be minus 2 over the square root of 61h minus 30 over 61h squared, all divided by h. As we've done before, we can go ahead and cancel out the limits. Or cancel out the h's. And so we get minus 2 over the square root of 61 minus 30 over 61h. Now we go ahead and evaluate this limit through direct substitution, and we get minus 2 over the square root of 61. Okay. Questions on that computation, folks?
Well, actually, could you scroll up just a little bit?
Uh-huh.
Just a second. All right, that's good. Thank you.
Okay, so just to emphasize again what we did, we said we took this a coordinate here, which was the x coordinate 2, there's 2, and then we nudged a little bit in the x direction, but proportional to how our unit vector was created. So we moved it a little bit in the x direction proportional to the x component of our unit vector. Then we took our b value, which is our y coordinate, and we added to that a nudge in the y direction, yes, but it's proportional to the y component of that vector u, directional derivative. Okay? And then we looked at, well, how did that change the corresponding z values, the output values, when we do that? And so what we find is that as we move in the direction of this vector u, which is the same as the direction of 5, negative 6. So as we move in the direction of 5, negative 6 in our domain region, we would expect our corresponding y value, or corresponding z values, our elevation, to drop by that ratio. Okay, so let's go ahead and give an equation for the tangent line at the surface at that point in that negative 5, negative 6 direction. Okay. So what have we just shown? Well, if we wanted to come up with the equation of tangent line, what do we need? We need an initial point, plus we need to say how we're changing as we move in that direction, right? So for our initial point, I think the correct first choice, or the correct choice for that would be where we started from. So that would be the coordinates. And so our x-coordinate was 2, our y-coordinate was 3, and then if you check that, you would find that the z-coordinate is 4. Okay. And then what we find is that if we were to step, how far do we step in the x direction? If we were to step in the x direction 5 over the square root of 61, and we were to step negative 6 over the square root of 61, that would result in a change in a step in the z direction of negative 2 over the square root of 61. And there we have our tangent line through this surface. It's a tangent line that moves in the direction of that vector. Okay? Another way you could denote this that I think is a little bit easier on the eyes is if we just went ahead and multiplied everything by the square root of 61, then you would see that, hey, as we step 5 units in the x direction, we go back 6 units in the y direction. That results in a drop of 2 units in the z direction. Okay, so let's go ahead and look at the this what we've just done here. Well, first of all, let me check. Are there any questions on the computations?
I think I'm just not all the way caught up. But how did you got your? I see that you got the -2 over root 61. But how did you get the other slopes, the other v's?
Well, look at this is so another. Put this another way, Xavier, is we could say that's r of t. If you wanted to give an equation for this, would be a b f of a b. That's how you find the that vector plus t times, and then what was this? So the way I did it initially, that was u1, u2, and then the directional derivative in the direction of u at ab. So you said, how did I get, you saw how I got that. That was that directional derivative answer. But how did I get u1 and u2? Well, those were the units of the directional derivative that I initially stepped in. Yeah, great question. Great question. In fact, I wish I'd put that in. I wish I'd written something like that and put it in your notes. So maybe add that somewhere. Yeah, other questions on that, folks? Can you all see that? Do you guys see, I see some people squinting. Do you want me to zoom in on something?
How did you go from those u values to 5, -6, -2?
Yeah. So, folks, these are not the same lines. So maybe I should give this a different name here. Maybe I should call this one. You could use this line or you could use this line. How about that? Because remember, all you need for a line is a point and a direction. And so once I found this directional vector, I could use any scalar multiple of that directional vector as well. So Hosanna, I think you asked the same question. So it's not that, don't think of it as I took this line and manipulated it. It's that this is another vector in the same direction. Yes, they are different only by a scalar, and so they are the same line. So these two lines differ only by the direction vector, but the two direction vectors are parallel to one another, so it's going to give me the same line. Yeah, great question. Other questions, folks? Okay, so let's go ahead and look at this in our CalcPlot 3D. Okay. So here, I want to first orient you. Here's our surface. That's the graph of that curve. That's the x times y minus 1 function. Okay, and here you can find the point. You see in black here, I've labeled the point that I want to compute the directional derivative at. Okay. So I think something that's helpful to think of is let's go ahead and just put ourselves back into the xy plane for just a second. So let's take this off. Let's take this off. Let's just put ourselves into the xy plane here. So there's the xy plane. And there's the point on the xy plane. Okay. And here's our direction vector in the xy plane. Right? That was that vector. You can see I just highlighted that was that direction vector 5, -6. So what we need to do is let's first of all give that as a unit vector, which I think is up here. Yeah, so there's the corresponding unit vectors. Everyone see the vector in blue that just popped up? There's the corresponding unit vector. But I think it makes more sense to think of it as being that vector. Let's see, is that what I want? Yeah, that vector in the plane right there. Okay. So finally, let's go back to our surface. So one way we can visualize this is there's our surface, and not that one. So there is that unit vector, but I've moved it up onto the graph, right? So I've moved it up onto the surface. So what I'm saying is that if I were to step a little bit in this direction, what would and I stay on the surface, what would my y values do? Okay, and you could almost visualize the answer from here. You would expect that if you stepped along in the direction of that blue arrow, would you be going uphill or downhill, folks? Can you see it from the image? Okay. it might be helpful then, if you're having trouble seeing it, let me put the plane that slices through in that same direction. Do you see that that plane slices through in the same direction as that unit vector? Okay. And so one way you can look at it is when I take that plane and slice it through the curve, slice it through our surface, it creates a curve here that I've just put in brown. Okay. It's a little hard to see that brown curve, so I'm going to take the plane off. So there's the curve that's formed by taking the plane in the direction of that unit vector. And now what are we going to do? Our task is to find the slope of the tangent line through the curve that's created by the plane intersecting our surface in the direction of our unit vector. Okay. And sure enough, the slope of this line is -2. If I were to step out 1 unit, I would expect to drop down 2 over 61 units. 2 over the square root of 61 units. Okay. Or another way, if I were to go 5 units in this direction, and then in the x direction, and then -6 units in the y direction, I would expect my curve to have dropped by a total of 2 units there. So anyway, you've got the code for this. You can play around with this and see what this all looks like. Are there any questions about what we just computed here with our directional derivative? Still digesting it? Okay, let's just work another example. But before we do that, we want to be able to do this in a faster way, right? So what we don't want to have to do is return to the limit definition every time. So we'd like to come up with another way of computing this directional derivative. Okay? So one thing I want to point out is that when we were doing this, at some point we saw this expression right here. The limit as h approaches 0 of 2 times 5 over the square root of 61 h plus 2 minus 6 over the square root of 61 h minus 30 all over 61 h squared. We saw that in the middle here, right? And the key to understanding a shortcut way of computing this is in this step right here. Okay. The first thing I want to do, let me shrink that down a little bit. So the first thing I want to do is break this limit up as just 2 times 5 over the square root of 61 h plus 2 times minus 6 over the square root of 61 h all over h plus the limit as h approaches 0 of negative 30 over 61 h squared over h. And these are called, this piece right here, the piece that I just peeled off, are the higher order terms of this. Those higher order terms will always go to 0. Okay. So whenever you do one of these problems, you're always going to have a piece that looks like this. Okay. And something worth noting here, this is actually not just something worth noting, this is the key to it, is that if you were to take the partial derivative of our function f with respect to x and you were to evaluate it at the point where we're at, you would get out a 2. And if you were to take the partial derivative of f with respect to y and evaluate it at the point where we're currently at, you would get out a 2. This 2 right here, I'm going to underline it once, is this 2 right there. And this 2 right here that I'm underlining in green, that's that 2 right there. So another way we could write this, after we're done computing the limit, is we could break this down as the vector 2, 2 dotted with the vector 5 over the square root of 61, comma, negative 6 over the square root of 61. Where this first 2 is the partial derivative of f evaluated at our point, taken with respect to x. Oops, I want 2 comma 3 there. And the second component is the partial derivative with respect to y, evaluated at our point. And this is, I'm just going to be a little more abstract here and put, that was our x component of the unit vector, u1, and that was the y component of our unit vector, u2. So, let me give you a chance to get caught up on that.
For the 2 that's underlined in green.
Yes.
The one in the red 2. What is that saying? Is that 2 times negative 6 over root 61, 2 plus?
That's a times. Yeah, that's a times there.
It's times. Okay.
Yep, great question. So that's just from this, Xavier, what I did was I just highlighted this part right here. And that would have simplified down to 2 times 5 over the square root of 61 plus 2 times negative 6 over the square root of 61. And what I'm pointing out is that that's not a coincidence, that you will always have these 2 components. Whenever you do this, you'll always have these 2 components of your unit, the unit vector that's the direction you're stepping in. So we could think of it as a cross product. So you've got something times the first component plus something times the second component. So you could think of it as a cross product, or excuse me, a dot product with your unit vector here. The question here that I don't think I've answered is how come these happen to be the partial derivatives evaluated at the point where we're currently standing. And that's something that I probably won't get to today, and I probably won't prove just because I fear we're running out of time. But the idea is that once we've done this, let me just keep jumping into it, that if I give you a function f of xy differentiable at ab, then the directional derivative in the direction of u, so rather than writing this and doing this limit definition that we just did, we can find that simply by computing f's of x of ab, comma, f's of y of ab. The partial of x evaluated at ab, and the partial of y evaluated at ab, and we're dotting that with the component vectors of our directional vector. Okay. Now, we're going to be using this expression right here. We're going to be using this and likewise the same thing, but without the AB being evaluated, so often that we want to give it its own symbol. Okay. So we're going to introduce this symbol here. It's our symbol for what we call the gradient. If you want to actually give a name to the symbol, it's called nabla, and you can think of it as drawing an upside down delta. Okay, so if you like, an upside down triangle, I guess. Okay, it's an upside down delta, letter delta. Okay. And so we're going to use this thing so much we want to give it a formal name. So here we go. So given a function differentiable on some neighborhood, the gradient of f is the vector valued function, which is defined by gradient of f is equal to partial f's of x of xy, comma, partial f's of y of xy. Okay. So this is a brand new symbol here, folks, the gradient symbol. Okay. One thing that I think is absolutely critical you realize is that whenever you see this, it's kind of hard to see it. This is a what, folks? What type of object is this?
A vector?
It's a vector, and actually it's a vector valued function.
I'm sorry. I think I'm still caught up on the last little section. I know we've moved on, but I'm super confused.
Okay.
For the 2, that's the for the tangent equation that would go into the B section vector.
No. The 2 is what, so I'm asking you to take, and you can check this, if you took the partial derivative of this original function with respect to x and plugged in the ordered pair 2, 3, it would output a 2. And if you took the partial derivative of our original function with respect to y and plugged in the point 2, 3, it would also spit out a 2. So this vector right here is the thing we just defined. The partial derivative evaluated at the points that you're working with.
So is 2 a point?
No, it's a vector,
It's a vector.
as we've written it here. And where did it come from, Xavier? I think one of the things is you're looking back at the last problem. We're talking about this new thing here, which is where that piece comes from. If you compute this for our problem, you would get 2.
Okay.
So if you were to compute the gradient for our particular problem at the ordered pair 2, 3, it would output 2. So let's jump into this part right here. So another way we can give the definition of our directional derivative then is that du of f of ab well, that's fine. Du of f of ab is equal to the gradient of f evaluated at ab dotted with the directional vector u. And this is how we're going to compute this from here on out. This is how we're going to compute our directional derivative from here on out. Okay. In other words, if you want to compute the directional derivative of f in the direction of u, you're going to take the gradient of f dotted with u. Okay, so let's go ahead and jump into an example. So let's go ahead and do this question right here, where we're asked to compute the directional derivative in the direction of, well, we're asked to compute the directional derivative of f at 3, 1 in the direction of this vector here. Okay. So the first thing we need to do is we need to find its corresponding unit vector, which is going to be the vector 1 over the square root of 2 comma minus 1 over the square root of 2. Okay. So just because oftentimes these aren't given to you in unit vectors, that's why I'm making us do the work of adjusting them. So now let's go ahead and compute the directional derivative in the direction of u of our function f at the point 3, negative 1. So if I lost you on what we did before, this is kind of the take-home point. Okay? Rather than returning all the way to the limit definition like we did in our first example. Where's my camera not on? Rather than returning to the limit definition of the directional derivative like we did in our first example, we're going to use this new alternate definition where we take the gradient of f evaluated at 3, 1 and we dot it with the directional vector.
Is it going to be 3, negative 1?
Yes, it is. Thank you, Aya. Good catch. Okay. So before I finish out this problem, I need to compute the directional, the gradient. So if I go compute the gradient of f, that's equal to negative, well, so in order to compute that, let's see here, let's write it this way. That's capital F sub x, comma, capital, we're using lowercase here. So it's f sub x, comma, f sub y. So let's go ahead and compute f sub x, partial derivative with respect to x of this function. And that's equal to minus 2x over 10 or minus x over 5. Doing the same thing, computing the partial derivative with respect to y.
Isn't it plus y squared over 10?
Yes, it is. Thank you. I missed that. Was dependent on x as well. Plus y squared over 10. Thank you, whoever pointed that out. And then if we go to compute the partial derivative with respect to y, we get 2xy over 10, which simplifies to be xy over 5.
Sorry, could you just back up a second? Just moving too fast. How'd you go from negative 2x over 10 equals negative x over 5 plus y squared over 10?
This should have been negative 2x over 10 plus y squared over 10 equals that. Sorry about that, Xavier.
All right, thank you.
I missed the, I thought this was just a y squared over 10, and I missed the x when I was...
And I'm just thinking slowly.
That's all right. I'm making a number of mistakes myself. All right. So now we're going to evaluate these at their respective points. So f sub x of 3, negative 1, that would be negative 3/5 plus negative 1 squared over 10, which is negative 6/10 plus 1/10, which is negative 5/10, or negative 1/2. If we do the same thing here, the partial derivative with respect to y evaluated at our point is 3 times negative 1 over 5, or negative 3/5. Okay? So, we're now in a position to say what this gradient is up here. So this is equal to, we just found that the gradient is the vector negative 1/2, comma, negative 3/5, dotted with 1 over the square root of 2, comma, minus 1 over the square root of 2. All right, so folks, I know that we've been doing a lot here. I want to make sure that everyone feels comfortable with what I just wrote here, given our new definition, given our definition of the gradient, or excuse me, given our definition of the directional derivative at AB is the gradient at AB dotted with our unit vector. So given that definition here, does everyone see what we just did in trying to compute this directional derivative? Anyone have any questions on that? Thanks. Yeah, folks, give me a thumbs up if you're good. Because if you're not, then I really want to go through it with you right now. Because it's going to keep getting more complicated as we go. Okay. So now we just need to take this dot product. If we compute this dot product here, let's see here, that would give us minus 1 over 2 square root of 2 plus 3 over 5 square root of 2. And if we were to combine these together, folks, I'm just going to go ahead and do it. It's just simplification. We get the square root of 2 over 20.
I think I have a question from
Yeah.
the very beginning. Just how did you get the u? The unit vector.
Okay, so what's our directional vector, Xavier?
Oh, 1, 1. Okay, I'm looking at 3, -1. Okay, I see how you did it.
Okay.
So it's square root of 1 squared plus 1 squared, which is the square root of 2.
That's the length of the vector v, and then you divide by the length. Good.
Gotcha.
Great. Other questions, folks?
So what we just found is the z component of the direction we moved in the u direction through the points 3, -1.
Well said. Yeah. The only thing I would add is that that's the approximate change, because just like on a curve, if you step along the tangent line, that's how far you'll fall, but that's not quite exactly how far you fall on the surface. Or in our case, I guess, yeah, we got minus, what did we get for an answer? We got a positive. So in our case, you'd be rising. So if you were to step from our surface, you go to our surface, and if you were to step in the 1, -1 direction from the point that we're given, so go to our surface on the point 3, -1, you're going to step in the 1, -1 direction. If you do so, you would expect your z value to change by approximately the square root of 2 over 20.
Okay.
Put another way, folks, the more precise definition is to say we've got this surface here, whatever this surface is. We've got a surface. And if we go to a point on that surface, there's the corresponding xy coordinates. If you were to step in the unit direction, that would give you you could construct a plane through that, just like we did before. That plane would give you a curve through your surface, and if you compute the slope of the tangent line at that surface, or of that new curve there, that's what you've just found by finding the directional derivative. Okay? That picture is really bad. Again, the original book picture from the author is probably a lot better. Where, again, you've got your surface, you take the coordinates A, B in your domain plane, you step that direction, whatever your u is. That creates this plane here through our surface. If you were to intersect that plane with our surface, you'd get this black curve here, and what we've just computed is the slope of the tangent line of that black curve. Okay. What else did I say? Do you want to do anything else? No. We'll just look at this. Oh, shoot! I've got the picture right here. Let's just look at this picture real quick. So there's our curve. There's that surface, right? There's the surface that we were dealing with. You can see I just highlighted with the z there. Okay. So there's our surface in the xy plane at the point 1, 3. Does everyone see the point 1, 3 in our xy plane there? Or excuse me, 3, -1 in our xy plane there. We step in the unit direction of our vector. So we go to the right 1 square root of 2, and we go down 1 over the square root of 2. That gives us that new vector here. If we look at the plane that's formed by those two, so let's see here, where's our plane? Maybe I didn't draw the plane on this one. That's okay. Let's just put this up here. Another way of saying that is that you can see what I just did here is I projected our directional vector up onto the curve there. And the difference between, you can see I just put a little line there, the difference between these two vectors is our directional derivative. So as we step along this red vector here, our tangent line would rise by that directional derivative amount. Okay, that's that 2 over the square root of 20 amount. Okay. Jumping into page 5 here, folks. Because we're running out of time, we're not going to work through this completely, but I just want to show you here we've got a surface, okay, some sort of paraboloid in our XZ plane, or excuse me, we've got some sort of paraboloid, and we go to the point 3, 2 in the XY plane, and we find the corresponding Z value is 25/4. Okay. Then we look at what happens if we step in the U direction in that XY plane. So there's the U direction right here. I'm stepping 1 square root of 2, 1 square root of 2. Okay, I'm stepping in the direction of that vector right there. And then asking the question, what's the slope of that tangent line right there? Okay. The slope of that tangent line is what I get when I compute that directional derivative. Okay. Now I could have done this for some other vector, like vector v here. So if I go back into my xy plane, there's the vector v. Can everyone see that? Let me zoom on that. There's the vector v right there. Okay. If I step in that direction, okay, then the corresponding plane intersected with our surface forms a curve right here that I've just highlighted in green. And if I go onto my surface and I take that particular curve and ask, what is the slope of the tangent line right there? As I move in that U direction, okay, you can see that as we move in that U direction, we've got a negative slope. Whereas opposed when we moved in this, that V direction, we have a negative slope. Over here, when we move in the U direction, we've got a positive slope. Okay? The only other thing I want to point out here is that in this problem here, I'm asking you to compute d of 1, 0 of f at some point p naught. So at the point 3, 2. But if you were to go do the work for this, by computing our gradient, and our gradient, remember, is the partial of f with respect to x, comma, partial of f with respect to y. So our gradient in this case is 1/4 times 2x, comma, 1/4 times 4y. And then if we were to evaluate throughout, so anyway, what we would get is the gradient of f of 3, 2 dotted with the vector 1, 0. But if I dot this with the vector 1, 0, then all I'm going to get, all that's going to survive is this 1 times this component right here. Because the other component is 0, right? That component dies out. But that is just the partial derivative of f with respect to x evaluated at 3, 2. Let's take a moment to digest that a little bit. If I compute the directional derivative, what direction am I computing that for? That's moving how far? 1 unit, where? That's moving 1 unit in the positive x direction. But that's just the same thing as computing what, folks? The partial derivative with respect to x. Okay. So likewise, if I ask you to compute the directional derivative of the function f in the direction of 0, 1 at the point 3, 2, that's just the same thing as computing the partial derivative of f with respect to y evaluated at the point 3, 2. And so we see that our partial derivatives are, you could think of them as kind of subcategories of our directional derivatives. All right. So that's what I just said on the previous page here. So we just said that the partial derivative with respect to 1 comma 0 of a function f, the directional derivative is just partial f partial x, and the directional derivative in the direction of the vector 0, 1 of our function f is just partial f partial y. Okay. We're running out of time here, so what I want to do is we'll just ignore these two questions. And let's look at this demonstration here that I linked to. Okay, sorry that's taking so long to pop up, folks. All right, so here we've got our function. In this case, it's the function x squared minus y squared. Okay, that gives us this graph with a surface with a saddle right here. And I'm going to go ahead and move this point to 1 comma 1.5. So that gives us this point on the curve here. Does everyone see this red point right here? That's the same as this P right here on the contour plot. Okay. So I'm going to ask it to compute the directional derivative. And notice that it's currently doing the directional derivative in the direction of the x-axis. So it's actually calculating the partial derivative of f with respect to x from our point right here at the order pair 1 comma 1/2. Okay. Now, I could change, so here's our vector. So you can see the black vector here shown here is the vector u, which is our directional derivative. And this allows me to adjust it. Does everyone see that? So I'm changing my vector u here by adjusting the angle that I'm at. So for example, right here, you can see, let's see here. Yeah, so right here you can see my directional vector in black here. Can everyone see that? Okay. And it's pointing towards the saddle. And let me just ask you, if you're heading kind of in that sort of direction, are you going uphill or downhill? We're going uphill. How do we see that? Because it's computed the directional derivative for you, and it's saying that that's a positive slope there. Okay? As opposed to, if we go back this way, you can see here the black vector x, that's my directional derivative. Here's the corresponding curve, right? I was trying to change these. I can't change these colors. The parabola-shaped curve right here, that's the curve that's formed by the intersection of our directional derivative and our surface for the plane that corresponds to our directional derivative and the surface. And you can see that if we head in this direction, we're going to have a negative directional derivative. All right. Now, take a look at these values up here. This is currently at negative 3.1, and I'm going to rotate us about, picking different directions, and I want you to tell me when it gives the most positive value. When are we getting the largest value for our directional derivative, folks?
I think it was near that blue line.
It is near that blue line. And what is that blue line, Xavier?
Crap.
So it's pointing in the 2, -3 direction. That is our gradient at that point. Okay. So that's the gradient at the particular point we're at. And notice how do we normally compute the directional derivative, folks? We dot the gradient with our directional derivative. Okay? And in fact, notice right here where I'm moving along this contour line, notice that my directional derivative is very, very close to 0, and it would be 0 if I could adjust it, if I could fine tune it. So when my directional derivative, the black vector here, is perpendicular to the blue gradient vector here, that's when I'm going to get the smallest, or a value close to 0, because what's the dot product of two perpendicular functions? It's 0, right? So that's where my directional derivative is going to be the smallest. And conversely, when they're pointing in the same direction here, that's when I'm going to get the most positive value. Okay. So let's summarize what we just saw there, and then we'll get some of our properties of the gradient. So always when we go to compute the directional derivative of u of the function f, that is, by this new definition, it's the gradient of f dotted with u. But how do we compute a dot product? Well, one way we can do so is to take the magnitude of the gradient times the magnitude of u times the cosine of the angle formed between them. That's how we can compute a dot product. But this is just the gradient of f times the cosine of theta, right? How come?
Because that's a unit.
It's because, unit vectors, the magnitude is 1.
So the magnitude of a unit vector is 1 since u is a unit vector. Okay? Now, going back to that question that we were looking at, when is this expression is maximum when, well, what's the largest value the cosine can take on?
2 pi.
No,
1.
that's you're thinking of the input there, Xavier. The output, the largest output of the cosine of an angle
1.
is 1. So this expression is largest, first of all, when the cosine of theta equals 1, and that happens when theta is equal to 0. And instead of doing the principal angle here, we mean 0 less than or equal to theta less than 2 pi. So where is it maximal? At the angle 0. Put another way, that's exactly what we saw on this demonstration here. When our directional vector was pointed in the same direction as our gradient, that's where we got the largest directional derivative. In terms of thinking about hiking, that's where you're hiking the steepest. You're going to be hiking the steepest when you move in the direction of your gradient. And notice that our gradient is what in relation to this contour line? What angle does our gradient make with, if you were to put a tangent line here on your contour line, what angle is that?
90.
90 degrees. So your gradient is always orthogonal to your contour line, and you're going to get the maximal directional derivative when your directional derivative, that black arrow there, that's your direction that you're heading in. When your directional derivative is heading in the same direction as your gradient, that's when the directional derivative will give the largest value. Okay, so everything we've just said is summed up in these two these three statements here. Okay? So first of all, f has its maximum rate of increase in the direction of the gradient vector. Okay? And that maximum magnitude is simply the length of your gradient vector. Okay? And this should be your minimum rate of maximum rate of decrease. That's fine. Your maximum rate of decrease in the I'm sorry, folks. This should be the opposite direction of the gradient vector, which would be negative gradient f of AB. Okay. All right. Folks, we still have a little bit more to go with our gradient vectors, and so we'll work some more examples of that next time. But I want to show you real quick before we go here. No, this didn't print out anything. If we go to our exam review, you can see that down here I've added some problems. Let's see here. For the gradient and directional derivative. So here you can get some examples of problems to be practicing. Okay. So find the derivative, for example, of f at 5, 5 as you move in the direction of v. Okay. So there are some examples for you to work for next time. All right. So folks, next time we will spend just a little bit, we'll finish out the notes on this, and then I will take your questions from the exam review. Okay. So if you would, work as much of this exam review as you can. And you've got a key to the first 3 pages worth of questions. Okay. So you've got a key there that works through what I called that first pass. Okay. If you get stuck on those earlier problems, please try the problems corresponding to whatever topic it is you're working on, because those problems will be more straightforward. And I think that by working those, then you'll have a better grasp of whatever it is that's giving you trouble on that, what I called the first pass for the exam review. Okay. So again, just to summarize, for next time, work as much of this exam 2 review as you can. We'll finish out section 15.5, and then I'll take whatever questions you have. All right, folks, stick around if you've got questions. Otherwise, I will see you either at office hours or I'll see you on Thursday.
So, will the exam just be up to 15.5?